Section 5.3 is talking about maxima and minima for quadratic functions. So we use quadratic functions to model a lot of projectile motion problems. So throwing a ball, firing a gun, launching a rocket, anything that involves basically a projectile of some sort can be modeled with a quadratic. So questions that we can answer with a quadratic model are things like, well, how high is the ball or rocket at some particular time t? How long will it take it to reach a certain height y? What is the max height that it will reach? And so forth. In the last section, we used the standard form of a quadratic to locate the vertex. And specifically what you probably noticed is that the vertex is the highest point, or the maximum, if the parabola is opening downward. And it's the lowest point, or the minimum, if the parabola is opening upward. So that corresponds with, it opens down if A is negative, and it opens up if A is positive. And so if you have an upwardly opening parabola, then you have a minimum, and if you have it opening downward, then you have a maximum at the vertex. If you recall, when we completed the square, we found the vertex with respect to the general form as being at negative b over 2a and c minus b squared over 4a for the x and y coordinates of the vertex. And as I said, if a is greater than 0, the vertex is at a minimum. If a is less than 0, the vertex is at a maximum. Let's actually look at a quadratic. So if I give you the function 2x squared minus 3x plus 4, and we just use the form to locate the vertex, so h is negative b over 2a, substitute that in. A is 2, b is negative 3, so I have a negative of negative 3 divided by 2 times 2, or 3/4 for the x-coordinate of the vertex. The y-coordinate is just going to be the function evaluated at this x value. So k is f evaluated at h, or 2 times 3/4 squared minus 3 times 3/4 plus 4, which if you simplify the fractions down, and yes, there's a lot of manipulation here, right? 3/4 squared is 9/16, and then if I multiply that by 2, it's the same as 9 over 8 minus 9 over 4 plus 4. This simplifies to negative 9/8 because this is the same as this if I divided it by 2. If I divide 9/4 by 2, I get 9/8. So negative 9/8 plus 4, or 32/8 minus 9/8, which gets me 23/8 for the y value. Since we know that a is equal to 2, which is greater than 0, this is a minimum value for this particular parabola, and that happens to correspond with the point at the vertex of 3/4 23/8. For good measure, let's do one with a negative a value, so opening downward. F of x equals negative 3x squared plus 5x minus 2. So again, we're looking for the vertex value. So h is negative b over 2a, or in this case, since b is 5, we have negative 5 over 2 times negative 3 for our a, which gets us a 5/6. Again, you can find the y value by just substituting your h value back into the function. So negative 3 times 5/6 squared plus 5 times 5/6 minus 2. This simplifies down, so we have 25 over 12 and 25 over 6 minus 2. That simplifies down ultimately to 25 over 12 minus 2. 2 times 12 is 24, so 25 twelfths minus 24 twelfths, which just gets us overall 1/12. Since our a value is negative 3 and that's less than 0, we know we have a maximum at our vertex, and our vertex was 5/6 1/12. So, what I started with, I told you that we could model these projectile motion problems with quadratic functions. So, if you throw a ball on a trajectory, so typically when you throw a ball, it has an equation similar to this because of acceleration due to gravity. So you have negative 16t squared plus 3t plus 5 in feet, where t is in seconds. So first question is going to be, at what time will the ball reach its maximum height? So since f is a function of time, and f is the height of the ball, then what I'm looking for is the t value that's associated with the maximum height. Since our a value is negative 16, which is less than 0, we know the vertex is the maximum height. So all we need to do is find h, which is negative 3 over 2 times negative 16, or 3 over 32 seconds. What is the maximum height? So we substitute in our 3 over 32 into our equation, simplify it down, and we have 329 over 64 feet. So at 3/32 of a second, you'll reach a height of 329 over 64 feet. We can also use it for problems like maximizing area. If you only have 80 feet of fencing and you want to build the largest rectangular pen that you can, what will the dimensions be? So this is similar to problems that you were doing previously, where you were trying to build functions for area problems and the like. So again, we only have 80 feet of fencing, so the perimeter must sum to 80. So if I have 40 minus x, 40 minus x, x, and x, because what I did is I said, okay, well, I'll define two of the sides to be x, and then the other two sides have to be equal. But when I subtract 2x from 80 and divide by 2, that should get me the side that I have, and that gets me the 40 minus x for those two other sides. So the area of this is going to be, obviously, base times height, 40 minus x times x, or 40x minus x squared. So in this case, my a value is negative 1, which is less than 0, so again, the vertex is going to be a maximum. Again, I just need to find the value of h that corresponds to the maximum, or that corresponds to my vertex. So negative b over 2a, that's negative 40 over 2 times negative 1, or 20 feet. So x is 20. Well, but if x is 20, then 40 minus x is also 20. So my largest area is actually a square that's 20 feet by 20 feet, where the area would be 400 square feet.